Hello, my name is Matt McGinnis, and I thought since we began looking at DC circuits, especially ones that involve batteries, it would be a good time to look at how batteries work, especially your everyday battery, such as your AA battery, or even one that you would find in your car, which is obviously significantly larger. So the history of the battery can be traced back to Mesopotamia in 200 BC. In 1938, archaeologists discovered small terracotta pots which inside had a copper cylinder containing an iron rod in the middle. Now they believed that these pots were eventually filled with some sort of acid like wine or vinegar, and then that the pots themselves could produce electricity, so they were in fact an ancient form of battery. As to why they would need an ancient form of batteries, archaeologists and historians still debate why. They think the most probable reason would be that they wanted to attempt to gold plate things, because obviously back then gold and silver had very significant value. And then in 1799, Alessandro Volta created what we consider a more modern type of battery. His battery can be seen here on the right. This design is referred to as a voltaic pile, in which he stacked layers and layers of copper and zinc, putting an electrolyte between them, and together they were able to produce a current. Now the whole idea of a battery is based on these reactions called oxidation-reduction reactions. They're electrochemical reactions in which different elements exchange electrons with each other. So in chemistry we have cations and anions. Anions are elements which are far more likely to take electrons from other elements, whereas cations are elements that are far more likely to give them away. Now as you can see here in the picture on the right, reducing agents will give their electrons away to an oxidizing agent in a process called oxidation. They lose electrons. When you lose electrons, you eventually become more positive. Now the oxidizing agent takes electrons from something else. Now it will then eventually end up with a negative charge. In chemistry, we assign different elements things called oxidation numbers, and they refer to how an element will interact when it's in an oxidation-reduction reaction. For example, oxygen needs 2 electrons in order to fill its final valence shell. Now, in order to do this, it'll need to take the electrons from somewhere else. We assign oxygen an oxidation number of -2 most of the time, because oxygen is going to take 2 electrons in order to reach a total of 8 in its final valence shell. Inside of a battery, you'll find that there's a lot of different parts. It's separated into 2 different regions, the anode and the cathode. The most common anode and cathode pair is zinc and magnesium oxide, which anyone who's taken AP chemistry can tell you that magnesium oxide appears a lot. Now we divide these 2 things inside of a battery with something called a separator, and then we allow them to interact with each other using an electrolyte. When we turn on a device that uses a battery, or we plug it back into the wall, if it's a rechargeable battery, what we actually do is we cause the cation and the anion, in most common cases zinc and MnO2, we cause them to begin to electrochemically react with one another. This in turn produces a current because there's a flow of electrons from the anode to the cathode. The current then runs from cathode to anode. Along the way, we have created a way in which this current can then be passed through what is referred to as the load. This load is what is being powered by this battery. So whether you're using your Game Boy or your cell phone, the load is the series of circuits or whatever it is that the current passes through in order to power the device. Now, in the case of a common everyday battery, like a AA battery, a AAA battery, or something like that, when all of the cation and anion have reacted with one another, at that point the battery no longer works because there's no more transfer of electrons. So, for this reason, the battery is, you could say used up, and you would throw it out. However, in the case of rechargeable batteries, like that found in your cell phone, even after all of the ions have interacted with one another, we plug it back into the wall. because we can use energy, the electricity found in the wall, to separate them back into their original form again. They are forced on the opposite sides of the separator, and then when we want to start using the device again, the electrolyte and separator begin to allow the interaction between the two to occur. Now, inside your everyday device, you usually find that, for example, your remote control, you usually find two batteries. Obviously, this remote control, let's say, is powered by the electric current that happens when you put the two batteries in. And then when you want to start using it, the remote control becomes the load, per se, for that battery. Now, in your everyday battery, obviously, there are positive and negative parts. So we've got the positive and the negative. So what that means is when you put them into your remote control, the electrons are going to flow from the negative side to the positive side. However, this begs the question, why do we bother putting our batteries in the opposite direction from one another? And the answer can be found in the series circuits, which we've just begun to learn about. In a series circuit, the overall electric potential of the batteries can be added together, which means that it's going to produce a stronger current. So if we were to place two batteries together just like this, right next to each other, then it wouldn't actually have any effect if they're attached together and they're supposed to be producing a current in this direction, per se. It would have zero effect. So instead what we do is we stack the batteries in opposite directions from one another. This allows so that the flow can actually travel in one direction, go through whatever it needs to do, whatever, and come back. This creates a series circuit of the two batteries stacked next to each other in opposite directions. To put it in simply as to why we have to stack them into opposite directions, think about your flashlight. In a flashlight, you have a flashlight. When you remove the bulb, you put it inside of this large container. So in the container, you stack the batteries. You just drop them in one on top of each other. In doing this, you create a series circuit. Now, in order to save space, because remote controls typically aren't long and handheld shaped like your flashlight, they stack the batteries in opposite directions from one another in order to create the series circuit and allow the flow of electrons to occur. Thanks for watching. I hope you all enjoyed learning why batteries work, and I hope you also enjoy my little fun fact.